It's all part of it.
Okay. That could get fun. Well, thank you, Brian. I appreciate the opportunity to come up here. I am an extension agent from St. Mary's County, which, depending on the traffic, is either an hour and a half or 2.5 hours south of here. Hopefully, it'll be an hour and a half today. I've been an extension agent for, this is my 24th year, so I've been doing this for a little while, but this is the first time that I presented at the Fundamentals of Nutrient Management course. So looking forward to it. We only have about 45 minutes, so I'm not going to be able to cover everything. You're going to have to do some studying on your own, but I'll try to cover the important parts. It's been about, Brian and I were talking earlier, I think it was about 30 years ago that I actually took the nutrient management exam. So I don't remember everything that's on it, but I do remember a couple things, and I'll point those out. All right, so just to review, I know you guys have been sitting here for, is this a 2-day course?
Yeah.
Wow. Am I like the only person between you and leaving, or is there?
No, me.
Oh, okay,
I'm the
okay,
last
Kayla,
one.
that's good.
And Nicole.
So why worry about fertility? Well, obviously, crop production, food production depends upon fertility, but fertilizer is expensive, right? And don't we all want our hay wagons to look like that?
That's the running joke.
Yes,
Yeah.
or overrunning with corn on the combine. If you look at agriculture, I look at agriculture every day as really a miracle that we're able to support as much life on this planet as we can. And a lot of that has to do with the folks that are sitting in this room, your ability to make good fertility recommendations. And there's a lot of different sources of crop nutrients that we can use to meet those needs. We just heard about biosolids, and we use a lot of biosolids in Southern Maryland. Particularly the product that's really popular now is a product called Bloom. That is the exceptional quality Class A material that comes out of Blue Plains. Of course, there's the magic of legumes and their ability to fix nitrogen. And so we can get nitrogen from legumes. Of course, we have the organic forms that come from livestock manure. We're a big livestock state here in Maryland. So we utilize, in this area, we utilize a lot of poultry litter on soils that need it. And then finally, commercial fertilizer. And so I'm going to be focusing mostly on this component. The other thing, I got to put a picture up of my kid. So we also have a responsibility. Not only do we feed the world, but we also need to sustain our natural environment, protect that environment. We all enjoy the Chesapeake Bay, all the recreational benefits and environmental benefits that brings. And so doing a good job of understanding where we're at with what we're putting on that land can help us in that job. And of course, Maryland, I think, is one of the most progressive states in the country, not in the world. Some of the European countries are a little ahead of us, but in the country in terms of how we regulate nutrients, when, how much, how we put those on. So there's lots of different parts of the nutrient cycle. I'm sure this is all review for you. So when we look at the inputs, we're looking at mineralization of mineral material or nitrogen, organic nitrogen in the soil, fertilizer inputs, manure, feeds, infixation by legumes. We look at outputs, well, obviously what we take off the land in terms of crops, livestock products, other loss pathways. Leaching and volatilization are the two major loss pathways, and of course runoff. So adequate soil fertility is essential. We've known this for a long time. If you were living in the 1800s, this is what your fields primarily looked like. Why? Because we didn't have an adequate supply. You didn't call up your southern states and say, hey, I need 120 pounds of N and 60 pounds of P. You had to manage, and a lot of it wasn't understood. All of your nutrients were coming from organic sources, whether that be livestock, whether that be manure, waste. And this is the same field, okay, same land. The only difference, this was recently cleared. This had fertilizer or nutrient supplied. This did not, okay? So fertilizers, nutrients are essential to sustain life. So what is a fertilizer? There's actually a legal term and a technical term for fertilizer. Fertilizer in the state of Maryland is regulated. It's a regulated product. In fact, it's regulated right here in this building. There's a lab that tests to make sure that a fertilizer bag that says it's 10-20-20 is actually at least 10-20-20. Okay, so it's a regulated product. It contains at least one plant nutrient. We're going to go through all the examples. Some examples for might be ammonium nitrate, potassium nitrate. Just remember that no fertilizer material contains 100% of any one nutrient. So we don't have a product that's 100% nitrogen or 100% potassium. That doesn't exist. There are always compounds that contain another element. Thankfully, they're not. If we had pure N, that's an inert gas. Doesn't do us much good. You all are breathing it right now. If we had pure elemental P, it would ignite when you expose it to the atmosphere. And of course, pure elemental K burns when it comes in contact with water. So perhaps some of you had those experiments in chemistry class in high school. Where do they originate? Where do we get our fertilizers from? This is an important point. Synthetic nitrogen originates from the atmosphere. We're going to talk about how that works in the chemical process. That's really an amazing process. We'll get time to dive into that a little bit further, but it comes from the atmosphere. The other two sources, phosphate and potash, are mined. Okay, so they're mineral sources. P from rock phosphates, K originating from K-bearing materials, usually as potassium chloride or potassium sulfate, that we actually mine and dig out of the earth. Okay, both of those products. Now, nitrogen. How do we get nitrogen from the air and synthesize it into ammonia and then nitrate and fertilizer we can actually use? Okay? Legumes figured this out a long time ago. They have a symbiotic relationship with rhizobia bacteria that live in the root nodules, and they're able to fix that nitrogen. People figured it out about 1905. Okay? And the folks that did that were two German scientists, and I can never pronounce his name right. I'll give my best. Haber and Bosch. So Haber actually and some of his colleagues discovered the process of how you do it, and Bosch was the one that actually was able to take that process and scale it up to a commercial scale that we could actually use. Okay, why is it so important? About, depending on who you want to talk to, somewhere between 50%, 75% of our food production is based upon this process, our ability to synthesize that nitrogen from the air. It's enormously important to be able to sustain a population that's 8 billion, 8.5 billion people. Okay. High pressure chemical engineering is the process. We heat this up really, really high heat. We also have to do it under very, very high pressure, and we're using hydrogen that is derived from natural gas. Okay, that's what's used in the process to get the hydrogen ions to convert inert atmospheric into fertilizer or ammonia that we can actually use. Now, the downside of this process is that this was also kind of refined during World War I. Okay, the use of bombs and chemical warfare, and then it was modified and used exclusively, of course, in World War II. All right, any questions on that process? Also, what does this mean in terms of fertilizer prices, particularly nitrogen prices? The fact that it's reliant upon natural gas, a lot of heat, and a lot of pressure. What does all that take? Money. What kind of money? If you see high gas prices, what do you expect your fertilizer prices are going to be? High as well, because it's a very energy dependent process. So anytime we see an escalation in natural gas prices, we're going to see an escalation in the cost of nitrogen as well. Now, phosphorus and potash, where do we get those from again? In the earth, right. And phosphorus is kind of fascinating. There's a lot of different areas in United States. The primary location of our sediments are in Florida. We actually have some fairly large mines in Florida, but there are also located all over the world. Morocco has 75% of the world reserves of phosphorus. Now, the deal with phosphorus in Maryland, when we talk about phosphorus, what are we typically worried about? Not enough or too much? Too much in the wrong places, right? Worldwide, because phosphorus is a finite, a limited resource, we're worried 100 years down the road, we might not have enough. There's people working right now trying to figure out how can we get some of the phosphorus that we put down that we don't need back out so we could use it when we run out, okay? U.S. in places like Florida, we have reserves for probably last us 25, 30, 40 years, something like that. There's a little concern with the amount of reserves that are in Morocco. Why is that? It's just like when we're concerned about fossil fuels, when we don't have them and someone else does, and if those countries become unstable, that can be an issue for food production for us, because remember, we're relying upon those materials for food production. So right now we do import phosphorus from Morocco. Number one, it's a little cheaper for us. And number two, it prolongs our U.S. reserves. Okay, so phosphorus is mined from rock phosphate. Potassium is the same way. Most of our potassium is in Canada. And then we have some other sites, particularly Russia, Belarus, and then some other countries as well. But again, these are mined products. Energy inputs, these are very highly dependent on a lot of energy. Nitrogen is the highest, about 5% of the total consumption of natural gas. Phosphorus a little lower, and potash the lowest. You probably won't be asked about this on the test, but just to give you some background. All right, you will be asked about this. I can almost guarantee you that. We need to understand what a fertilizer analysis means, and this gets a little bit tricky. This bag is 5, 10, 15. Now, typically when we see that and someone says, what does 5, 10, 15 say? I automatically say, well, that's NP and K analysis. Am I right when I say NP and K? Yeah. Not technically, I'm actually wrong. And for the purposes of this test, you would also be wrong. So just remember that. N, P, and K is expressing it in the elemental form without any oxides on it, okay? So this bag actually contains 5% nitrogen, 10% phosphate, and 15% potash, okay? It's a 50-pound bag, so how do we go from 50 pounds? So we take 50 pounds, we multiply it by the percentage here, 0.05, gives us 2.5 pounds of nitrogen. Everybody kind of clear on how to, that's pretty simple math. So this bag contains 2.5 pounds of nitrogen, 5 pounds of phosphate, 7.5 pounds of potash. Okay, so you might ask, what's the difference between phosphorus and phosphate, and why do they make it so confusing? Well, I guess it's so they have something to test you on when you take the test. There needs to be at least a couple questions. You need to memorize this. Okay, it's not that hard. It's just 4 formulas, 4 numbers you have to remember. Nitrogen is expressed in its elemental form, total nitrogen. Okay. However, on the fertilizer bag, it's presented in the P2O5, the citrate soluble plus water soluble form. All right. So that's the phosphate, the oxide form. Same thing with potash, is presented as K2O. All right. We need to be able to convert between those two. So to go from phosphate to phosphorus in the elemental form, it's a simple multiplication factor of 0.44. We want to go the other way, and this makes sense. We have some oxygen elements attached to this molecule, right? We have 2 phosphorus and 5 oxygen. So obviously, if we want to go to just P, there's not going to be as much P in there because we have to take the oxygen and the 1 phosphorus off. Does that make sense? So it's a lower number. If we go the other way, it's going to be a higher number. So it's 2.27 to go from phosphorus to phosphate. Make sense? I can go through the fancy calculations and the molecular weight per mole and show you how we come up with this. That's not going to be on the exam, I don't think. And if it is, it's probably not worth that 1 point to remember how to do it. If you're really interested, you can look up on YouTube determining the grams by molecular weight of a molecule, and it'll take you right through that. We're not going to do that today. The equation to go from potash to potassium is the potash times 0.83. Remember, it's going to be a lower number. That's going to give you potash. To go the other way, you take multiply 1 by 1.20, and you'll get potash. Does that make sense? Everybody clear on that? All right, let's do an example. You have cow manure. Unlike biosolids, most livestock manure has potassium in it. Okay, so they say that the percent potassium is 0.5. What is the potash content? So what are we going to do? Anybody have a guess? So we take the potash, which is 0.5, times 1.20 is 0.6. So the correct answer is 0.6. Everybody see that? All right, let's try another one. All right. By the way, when you get a recommendation, what are recommendations given as typically in the real world? When you get a nutrient management plan, it says your corn crop needs 140 pounds of N, 60 pounds of, how many do this? Let's say it's 140, 60, 30. What would the 60 be? Are they talking about phosphorus or phosphate? It's phosphate. Recommendations are typically always given in the oxide form as phosphate or potash. So in the real world, we're always talking about phosphate or potash. But in the academic circles and for this test, you need to be able to go back and forth between the two. All right, so let's do this. Anybody have a guess? It's 60 pounds of phosphate are equivalent to how many pounds of peat? First of all, there's going to be a higher number or lower number? It's going to be a lower number. That's correct. Remember, we've got to take this oxygen off and that extra P off. So this is the conversion value. So 60 times 0.44 is 26.4 pounds of peat, right? This is going to be a multiple choice test. So if you're not sure, you know you can eliminate at least half the answers, right? We know it's not more. But just memorize those 4 conversion factors. All right, any questions on that? Very good. All right, let's talk fertilizer. If you are a farmer, if you are a practitioner in the field, meaning you manage a golf course or you have a landscape company or writing nutrient management plans, this is the type of information that really matters in the real world. First, we have ammonia, typically called anhydrous ammonia. Anybody here ever use anhydrous ammonia in Maryland? Anybody here? You've used it?
No, it was on a utility site.
Okay, very good. I don't know if we call that real world or not.
No, it was real world, real nasty world.
In Maryland, we use very little anhydrous ammonia. Across the country in the Midwest, they use a lot of anhydrous ammonia. Anhydrous ammonia is it's liquefied, it's under pressure, okay, so it's hazardous to deal with. It looks like when you're going up and down the road, they're pulling a propane tank, because essentially that's what they're pulling, is a tank with gas in it that's under pressure to keep it in the liquid form. As soon as you release it to the atmosphere, it goes from the liquid form into a gas form, okay? So what does that mean? To apply it, you have to knife it in under the ground. You have to trap it under the ground, or else you lose it all. In Maryland, on the eastern shore, they do use a little bit of anhydrous ammonia, okay? But in the rest of the state, there's a couple reasons. In southern Maryland, we simply don't have the infrastructure for it. Nobody sells it. And in western Maryland, they have more rocky ground, more slate, more cracks and crevices, and that gas is just going to escape pretty quickly. They also, I hear they have rocks up there, and you can imagine pulling chisel through rocky ground that sometimes might not work so well. So it's limited in Maryland, but around the country, it's used a lot. In fact, in the Midwest, it's often put down in the fall for the spring crop. It's the cheapest form of nitrogen that we have, by the way. That's why it's used so much. But you can scratch that off your list for Maryland. There's ammonium nitrate. Anybody ever use ammonium nitrate? You have any old tobacco farmers in the room? Kale, I know you've used ammonium nitrate. This was our favorite fertilizer for side dressing tobacco. We don't use much ammonium nitrate anymore. And why is that? What's that? Anybody have any guesses? It's not because we don't have tobacco anymore. We'd love to buy this if we could. Safety for what reason? Right, okay, so this is an oxidizer. It can be used to make bombs. Okay, it blows things up, and unfortunately, it was used. It's been used in a number of terrorist attacks, so it's tightly controlled. Now they've done some things because it is so important for tobacco production. They've tried to modify the formulation some, so it's not pure ammonium nitrate, and you can't. It's not as much of an oxidizer, but it's still very hard to get. So this you can scratch off your list as well. How about urea? I'm sure any farmer in the room has used urea. All right, here's urea. I actually did some show and tell. This is what it looks like. It's a white granular formulation. They make two types. Most urea is prilled. That means that it's almost a perfectly round little ball. You can also get this. It's what we call a granular that's not prilled. But this is urea. Okay, typically 44 to 46%. You all can pass that around. I wouldn't open up the bag. In Maryland, it's the cheapest, or one of the cheapest forms of nitrogen. Okay, what's the issue with urea? Okay, it's strong. That's not bad in itself. It can burn turf in particular or other crops. And in fact, if you look at corn right now, a lot of corn fields you'll notice it'll have brown on the leaves, and that's from either urea or UAN solution that's been put over top of it.
Does it line with anything else?
No. You're on the right track. Especially, this is the perfect time to talk about urea and the problems with urea. Urea is used for nitrogen on corn right now. There's thousands of tons that are probably being spread as I speak. It volatilizes. That's right. Okay. So if we apply it to the surface, urea can volatilize, and you can lose, up to 50%, if not more, to volatilization. Okay. So that's the issue with urea. All right, ammonium sulfate. I think I actually have ammonium sulfate. Turf folks, how many folks in here are turf folks? There's some turf folks here. You all probably love ammonium sulfate. Us agronomy guys, we love ammonium sulfate too. This is what it looks like. Ammonium sulfate, as you can see, is 21% nitrogen. But you get a little something else, maybe the name will tell you. Sulfur, it's 24% sulfur. So we would write that as 2100-24S. Okay, so this has a good bit of sulfur. Why are we worried about sulfur nowadays? Anybody know why sulfur is a problem? Sulfur is a secondary nutrient along with magnesium and calcium. You all had this lecture, right?
We talked about this.
Okay, so we're not getting sulfur from acid rain and from pollution anymore like we did 30 years ago. So we need to add, typically we're adding 20 to 30 pounds per acre of sulfur to most crops to supply the needed sulfur, and this is what we're using to do it. Okay. It's also good because it doesn't volatilize like urea. Now, what's the bad thing about ammonium sulfate when you would compare it to a urea product? There isn't a good. I wasn't thinking about that, but yeah, this is one of the most acidifying fertilizers there is. If you want to drop the pH, you use ammonium sulfate. That'll do it for you. I have a chart here in a little bit. The problem is it's expensive. Okay, it's about it's not double the cost of urea, but it's much more expensive than a product like urea. Okay. All right, and then we have UAN solution, or what we call in the field, we'd call this liquid N or liquid nitrogen, not like the refrigerant. But it's a mixture of urea plus ammonium nitrate, and this is a liquid formulation. It comes anywhere from 28 to 32%. They use the lower blends in colder temperatures. It doesn't salt out as badly. In this area, typically the majority of what we use is going to be a 3200 product. Okay, so this is what we call UAN. This is the liquid fertilizer that we often side dress with. Some less common fertilizers, but folks in the turf industry would be a little bit more familiar with these. So you have sulfur-coated urea. So that's basically urea that's been coated with a sulfur product and some other products, so that greatly slows the release of that product down. You have some products here, urea form and methylene urea, which have been mixed with formaldehyde. That also creates a controlled release, or what we call a slow release nitrogen, so it doesn't release nearly as quickly. Urea releases as soon as you get any moisture activated, it's going to release very, very quickly. Okay, and then you have these IBDU type products. Another typically they're a mixture of urea with this IBDU. I'm not going to try to say that. Even if I say it fast, I'll get it wrong. Again, slow release. I say these are often used in the turf and landscape industry. In the turf, well, first of all, there's a regulation that you have to use a slow release nitrogen. And secondly, it's better for turf industry if you don't have to make as many applications. Okay, so if you can do one application instead of it only lasting 3 weeks, it'll last 6 to 8 weeks. It's much more beneficial to you and the plant. All right, another one that I got some more samples. By the way, what I'm showing you are the most widely used in sources. So I have one more, and we can't use ammonium nitrate anymore, but we can use calcium nitrate. So calcium nitrate is a 15.5% nitrogen source, and it also comes with a good amount of calcium. I think it's about 20% calcium, although I'd want to look that up to make sure. So calcium, this is very good for vegetable producers that need that extra calcium. We also often use it as a side dress product for tobacco or other value-added crops. This is a soluble grade, so this is completely water soluble, so we can also fertigate with it. So we put this through the irrigation system for vegetable crops, for instance. So this is calcium nitrate. Who has the ammonium sulfate? Heard that back. They bring it back up? Oh, did I not pass it out?
You said one.
Okay. Here's calcium nitrate. One thing you'll learn quickly about fertilizers, there's some products you can't mix together. One of those examples, don't sit too close, Kelly, you can be our emergency response person.
I don't do that. That's Mike.
All right, so we're going to take ammonium sulfate and calcium nitrate, and we're going to put those two together. In the field, we'd never do this. Because there's a little bit of a reaction that happens, and this is going to turn into a nice gel, goopy product that's going to get hard on the sides over time. Typically doesn't sink too bad.
What? Ammonium sulfate and calcium nitrate?
That's right. See, we'd love to be able to do that because we get sulfur and we get calcium all with one run. And calcium nitrate, it doesn't volatilize hardly at all. But if you go to do that, you'll let this sit here and work for a while. Everybody else see the other products?
You're by the experiment.
All right. So, is the efficiency of all in fertilizers the same? You should know the answer to this. I just told you about urea, right? It volatilizes. UAN solution can volatilize as well. So it depends, but the real answer is no, they're not the same. Ammonium-bearing fertilizers or fertilizers that are converted to urea, you have volatilization losses that are possible. We're going to talk a little bit more about that and what we would do to control it. Now, let's talk about phosphorus fertilizer. So phosphorus is, again, where do we get it from? From rocks, rock phosphate, okay? Now, rock phosphate, in organic circles, there's a lot of folks that like to use, it's called brown rock or rock phosphate. We put it down. The problem with rock phosphate is it's not available. It's not soluble. It takes years upon years to become available to plants. So we have to treat rock phosphate to make it in a form that's going to be available to plants quickly. Okay, how do we treat it? We treat it with acid, typically phosphoric acid or sulfuric acid. And the number of times you treat it and what you treat it with is going to determine which of these products you get. Okay, so superphosphate is the first product you get, and then you get triple superphosphate. These two are not widely used. Okay. The next one is monoammonium phosphate. So that's where you take superphosphate, you mix it with ammonium, and you get this monoammonium phosphate, which is 1148.0. Okay, that is here. This is what it looks like, monoammonium phosphate. In Maryland, this is your source of phosphorus right now. The other source is diammonium phosphate. You all can pass this around. Diammonium phosphate, very similar and very similar process. It's just how they add the acid, how long they keep it in there and process it, and how much ammonia they add. Diammonium phosphate was very, very popular, but guess what? You can't get it this year. It's not available. Okay, but these two are widely used. Now, as a fertilizer source, what does that mean for you? If you get a recommendation for soybeans, do soybeans require nitrogen fertilizer as a rule? Soybeans are a legume, right? They supply their own nitrogen. Same thing with alfalfa. So we need phosphorus. Where are we going to get the phosphorus from? You call up the fertilizer company and say, well, I only have MAP and I only have DAP. So if you make a mixture of that, what are you getting with it? You're going to get some nitrogen with that as well. Okay. Typically, does that hurt anything? It does not hurt anything. Okay. The legume can still utilize the synthetic nitrogen that you put on it. It's just a matter of economics. Is it worth it for you? Is it cheaper to get the phosphorus with a little bit of nitrogen that comes with it? Or would it be cheaper to buy a single-made product that you have to ship in and is twice the cost? And typically the answer is you're going to use one of these blended products. Okay. There's also ammonium polyphosphate, which is a liquid product, a clear liquid product that's often used as a starter. You all talked about phosphorus, right? One of phosphorus's primary needs when you plant a crop is for what? Seed and development, root growth, to get that plant off to a good start. So starter fertilizers have a high percentage of what element? Phosphorus, right? So this makes a natural good starter fertilizer. Any questions as I go along? Yes, ma'am.
I don't know if this is particularly a question for you, but when we're doing the recommendations though for a farmer, they want to use that, like when they're planting soybeans, the recommendation is 0 for nitrogen. So is that going to get them in trouble with the regulations then if they still use that?
Well, that's where you need to pay close attention to the regulations. In fact, when we did the biosolids talk, if you noticed on the recommendation, she had a recommendation for soybeans of 50 pounds of N. So there's actually a prop code where you can put up to 50 pounds of nitrogen on a legume if you need it. Okay, particularly that's going to come from a manure. Okay, but yeah, it gets to be complicated when we look at the real world and then we look at what the regulations are and what you can actually do. Now, we can't go out and put like 200 pounds of nitrogen on a soybean crop. That would be a big no-no. All right, now common potassium fertilizers. Most widely used is muriate of potash. Okay, that's potassium chloride, 0060. The cheapest form of potash we can get. It's widely available. Okay, what's the issue with potassium chloride? Muriate of potash. Chloride. It has a lot of chloride in it. Some crops are sensitive to chlorine or chloride. Anybody know any of those crops? I'll give you a hint. We grew a lot of it in southern Maryland. Tobacco is chlorine sensitive, so we could not use muriate of potash. So there's always a special tobacco grade, and it uses sulfate of potash or potassium magnesium sulfate or potassium nitrate. The sulfate of potash is also widely available. It's more expensive. It doesn't have the chlorine in it. Some folks also have an issue with chlorine because it's a salt. And there's some folks that think if you put too much chlorine down, you can actually have issues with salt burn of that crop. You do have to be very careful if you were to use muriate of potash in a side dress. In a starter fertilizer that you put down very close to the seed. Now I'm nervous. Nicole just walked in. The last one is potassium nitrate. Potassium nitrate is the same story with ammonium nitrate. It's an oxidizer. It can be used as an explosive, and so that one is not available anymore. Again, they've done some some things to the formulation. Instead of a 13044, now you can get it as 11046 with some special regulatory requirements. But for the most part, it's not widely available anymore. All right, there's different types of fertilizer. You all gonna have to keep me on time. I don't have any idea when I started,
Give me a
how much time I
second.
have left. Solid types, we have granular, we have bulk blend. That's a little bit confusing. Granular products are typically mixed in a liquid state and dried, and so every granular has almost the exact same, every granule has the same amount of nutrient. And then we have our bulk blend products, so that's where we take these products, we mix them all together, we blend them up just like you were making bread, and the resulting product is, or the mix is called a bulk blend, okay? And it's going to have the percentage of nutrients or whatever you blended it to. For liquid or fluid, there's what we call solution, so that's for soluble grade products that are in solution, and then we have products that are just suspended or a slurry. Typically in this area, we use solutions, okay? Hopefully it's a solution and didn't salt out. So bulk blended fertilizer, which is by far the majority of what we use in Maryland. Every large fertilizer distributor has their own bulk blending tank. If you come in and say, I have 45 acres of corn, I need to put on 100 pounds of nitrogen, 30 pounds of phosphorus, and 80 pounds of potassium. They're going to bulk blend up using urea, ammonium sulfate, muriate of potash, and some MAP. They're going to put those four products together. They're going to mix it up. This is just an example here to create that specific blend that you need. All right, does that make sense? They might also need to add a little bit of filler. So that could be a clay-based product, that could be sand, other products that are really cheap and easy to buy to make up the weight. All right, so what's the rest of the stuff in the fertilizer bag? Well, it depends. Some products don't have anything else in them, and that's the case with muriate of potash. Muriate of potash is actually what we talked about, potassium chloride, which is 52% potassium and 48% chlorine. So what else is in the bag? That's 100%, so nothing, okay? This is all muriate of potash. You don't need a filler. And Trish would always, I think, emphasize this. There's a difference, you know, if you make meatloaf, you're mostly making that for a protein, right? But you're also going to get some fat, some water. Well, you put oatmeal and breadcrumbs in there. What is that for? That's a filler, right? It makes it go further. Okay, it might make it taste a little bit better, but you can feed more people with that. That's really a filler. If we look at muriate of potash, is there any filler in that? No, it's all either potassium or chlorine. Okay, any questions so far?
You've got like 5 minutes.
Oh my gosh, wow.
Yeah. So really cover basic line stuff.
Yes,
We've talked about a lot of those concepts once already.
very good. There's some terminology that you should somewhat be familiar with. This is pretty basic stuff. I don't have a lot of time, so I'm gonna skirt through some more. You need to be able to do a basic nutrient calculation, okay? So you're gonna get a recommendation for pounds per acre. Let's look at an example here. You get a recommendation that you need 90 pounds of potash, okay? No P or N. You're gonna use muriate of potash to meet that need. So how do you do that actual calculation? It's pretty simple. You start with your 90 pounds of needed product. It's a 60% by analysis, so that you express that as a decimal. So again, just move that decimal point over 2 places, so it's 0.6. 90 divided by 0.6 is 150 pounds to meet that 60-pound rec. Everybody follow that? Pretty simple. I think you guys can get this. So 60-pound rec, again, this time we're using ammonium sulfate. So 60 divided by 0.21 is going to get you 285 pounds of ammonium sulfate. It can get a little bit more complicated in the real world. If I'm fertilizing orchard grass, I want to use a little bit of sulfur on there as well, okay? So if we have two nutrients we need to solve for, we're going to start with the priority nutrient, in this case sulfur. I need 20 pounds of sulfur. So I solve for that. I'm going to use 83 pounds to get my sulfur, okay? 20 divided by 0.24 gives me 83 pounds. Then I need to figure out how much nitrogen am I getting from that ammonium sulfate, which is 17.5 pounds. I go to the next step, and I solve for the remaining nitrogen. So remember, my rec was 60 pounds. I'm getting 17.5 from the ammonium sulfate. That means I need 42.5 from urea. So we take 42.5 divided by 0.46. That means I need 92 pounds of urea. That makes sense? All right. We're going to skip this, I think, for time. Just realize there's different ways that we can protect fertilizer that we put down. Okay, we have nitrification inhibitors. So those are products that try to kill or limit the efficacy of the bacteria, nitroprin that's used to go from ammonium to nitrite. And we also have urease inhibitors. That's what this is. This is urea that's treated with a urease inhibitor. Urease inhibitors, again, prevent the enzyme urease from working until we can get this urea into the soil through rain. Okay. Typically, we don't need a urease inhibitor if it's cool. If we're going to incorporate it, if we're expecting rain soon after, or to a limited degree, if we band it, or what we call side dress it in a banded formulation. If you spread it over the ground in windy, hot day like today, you're going to lose a significant amount. There's also other technology where they use semi-permeable membranes. ESN is an example of that, where they coat it with a polymer that lets water in very slowly. And then we have products like a veil, which actually protect that phosphorus from other elements like iron or aluminum or calcium. All right, we're going to talk about liming really quickly because I'm running out of time here. Liming is the cheapest fertilizer we can buy, and it's really, really important because it affects the availability of all other nutrients. This is the classic chart that we put up. You can see that if we get too high of a pH, we can run into problems in this area, particularly with manganese and iron. If we get into too low of pH, two things happen. Aluminum becomes widely available. Aluminum is toxic to root growth, and a lot of our other elements become deficient. Molybdenum, for example. Phosphorus becomes bound by aluminum, not available. Potassium becomes less available. Calcium. So you can see the sweet spot here is right in this area. That's why most crops require a pH 6.2 to 6.8. Okay. This is aluminum toxicity for alfalfa. Alfalfa likes a high pH, 6.8 to 7 typically. You can see what happens when we grow it in a lower pH versus a field that's been treated with lime. We'll skip over that real. Oh, I do want to mention this. So fertilizer does typically acidify soil, and you can look. Here's ammonium sulfate. This is the pounds of lime required to counteract every pound of that fertilizer that we put on. So you can see that monoammonium phosphate and ammonium sulfate are the two largest, but typically all nitrogen sources are going to acidify that soil over time. Okay, let's keep going. All right, we're going to talk quickly about liming, okay, and how we determine a lime rate. So lime rate is going to be dependent upon your initial pH that you start with, the target pH of that crop, so the desired pH, and finally an estimate of reserve acidity. There's two ways to do that. In Maryland, the nutrient management software uses soil texture and uses the physiographic province that we're in, whether it be the coastal plain, the Piedmont, or plateau, the valley area. I'm always dealing with coastal plain in southern Maryland. So this gives us information about the kind of clay, and the soil texture is the amount of clay. Okay, this is kind of an estimate for for CEC or reserve acidity. There's another way to do it, and that's with soil buffer calculations you can get done at the lab. We don't use this in Maryland, but you can. This is another calculation, and neighboring states actually do use this for determining lime rates. Just realize that the heavier the soil, okay, so the more clay content in the soil, the more resistant to a pH change that soil is going to be. Does that make sense? So the more lime that's going to be required. If you have a sandier soil, like on the coastal plain regions, it doesn't take as much lime to affect a change. That pH is also it's going to go up more quickly. It's also going to go down more quickly. So your roller coaster has sharper, more frequent peaks. Okay, and this is demonstrated here on the amount of limestone that's needed to affect a pH change. All right, when should you apply lime? Well, you want to apply lime before you actually need the change to occur. Typically, it's going to take 2 to 6 months for that lime to fully react with the soil, typically regular ground limestone. All right, there's different types of lime. The two you're going to be working with the most are going to be calcium carbonate. This is standard ag lime, often called calcite, high cal lime, or just standard limestone. It's made up of calcium carbonate, typical value, CCE value of 100%. Dolomitic lime, on the other hand, has calcium and magnesium in it, okay? Depending on where you live, you can get either of these materials in Maryland. Dolomitic is a little bit more widely available in this region. You have to drive a little bit farther to get the calcium high cal lime or the standard ag lime. There's other limes. We have burn lime or quick lime. This is calcium oxide. It has a much higher CCE, but this is typically very expensive. It's also caustic and not something we typically use. And then we have builder's lime or hydrated lime, which is calcium hydroxide. It's 136%, so it's even more. It's a little bit more effective than standard lime. I don't think this is going to be on the exam. Just remember, it's not the calcium that's really doing your work when we're liming soils. It's the carbonates, okay, by hydrolysis. Their interactions by producing these hydroxide ions that then interact with water or hydrogen ions to create water. So it's your carbonates that are actually doing the work. The two things that are going to affect your liming material and how fast you're going to, and how effective that liming material are going to be, it's going to be your particle size. Okay, the finer the grind, the more effective the limestone, and the chemical composition of that material. Okay, so we actually, when we're evaluating a limestone, we use a sieve, and we see what percentage is passing through a 20, 60, and 100 mesh screen. Basically, the finer the material, the better it works. So if it passes through a 100 mesh screen, you can see it's very effective very quickly. You can see that it's fully effective in about 3 months' time, and then gradually goes down. Whereas we have an 8 mesh screen, you can see that it's not very effective at all. Okay, and no lime is down here. We're going to continue that roller coaster ride down. So what does that mean? When we're evaluating limestone, there's an actual formula that you can use. The percent retained by that 8 mesh sieve, in this case it's 5%, has no effectiveness. We don't count the value of that limestone at all. Does that make sense? It's basically too large to react with the soil. The next, the percent that passes through this 8 mesh sieve, but's caught by the 60 mesh sieve, is 14%, and that has 50% effectiveness. So that's only 7% actually effective in the limestone. That makes sense? And then anything that passes through the 60 mesh sieve is 100% effective, and so we're at 81%. So the total effective value for that particle, based on particle size, is 88%. You following me? So if we have 2,000 pounds of that lime, and we divide that by 0.88 times 100, or just 0.88, we get 2,272 pounds of lime to equate to a 2,000 pound 100% calcium carbonate equivalency. Okay, so this is the amount of lime we'd actually need to meet that 2,000 pound rec. Does that make sense? Okay. I think we'll skip this one. This is basically doing the same thing. Oh, I do want to talk about one more thing. I guess I can use this one. We also need to take into consideration the calcium carbonate equivalency. So in Maryland, we typically are going to be basing our recommendations on calcium carbonate equivalency versus oxides. You can do either way. So standard ag lime, high cal lime, has a standard value of 100 CCE. So we try to evaluate all other liming materials. When you get a recommendation out of Newman software, for example, it's assuming that you have a 50% oxide lime that has a 100 CCE value of 100. So it's 100% effective. If you go above or below that, you need to adjust your liming recommendation to make up for that difference. Okay. So in this case, it's only 90% effective. So it has a CCE value of 90 instead of 100. So you have to increase the amount of lime that you're actually going to apply. So in this calculation, they looked at the particle size. So it has an 87% fineness value and a CCE value of 90. So the effective neutralizing value is 90% times 87% is 78.3% effective. That makes sense? So if we do that calculation, we take 2,000 pounds divided by 78.3 times 100. That limestone is, you have to apply 2,554 pounds. You get the same value as a 100 CCE fine limestone. Okay. All right. With that, I know we went through the lime part fairly quickly. Are there any questions? And this still didn't react very well yet. I think it might be too dry. I think we might need to put a little water in it.
Oh, boy.
We're doing chemistry experiments up here, Nicole.
Do you have contact information if we have questions?
Yes, I'm sorry. It's probably the best way is my email. So that's bbeale@umd.edu. Probably the easiest way to do it is put it here.